In the vast tapestry of scientific discovery, some of the most profound revelations arrive not with a grand fanfare, but as an annoying, persistent whisper. For two young radio astronomers, Arno Penzias and Robert Wilson, this whisper manifested as an inescapable, maddening hiss. It was the year 1964 in Holmdel, New Jersey, and their work was far from the celestial. It was deeply rooted in the pragmatic, almost mundane realm of Cold War technology. Their mission, funded by Bell Laboratories, was to refine satellite communication, a crucial component of the era's frantic technological arms race, using a massive, repurposed horn antenna. This very antenna, a magnificent structure designed initially for the pioneering ECHO satellite project, which bounced signals off balloon-like satellites in orbit, was intended to be a silent, precise instrument. Yet, no matter where Penzias and Wilson pointed its 20-foot aperture, no matter how meticulously they calibrated their equipment, a faint, unwavering noise persisted. This wasn't the expected radio chatter from distant galaxies, nor was it local interference. It was a uniform, omnidirectional static, emanating from every direction, equally strong day and night, season after season. It became an infuriating phantom, a constant irritant in their pursuit of clear, crisp satellite signals. Their efforts to eradicate this stubborn anomaly were both exhaustive and, in retrospect, comically meticulous. They checked every connection, rewired circuitry, and even painstakingly removed every trace of bird droppings from inside the giant horn. These avian deposits, a thick layer of what they humorously dubbed white dielectric material, were a prime suspect for noise contamination. They even considered the possibility of radio signals from the nearby New York City, or perhaps atmospheric disturbances, but every conventional explanation failed to account for the signal's peculiar constancy and universal presence. This was not merely background noise, it was an intrinsic part of the data, a signal that refused to be dismissed as mere equipment malfunction or environmental interference. But unbeknownst to Penzias and Wilson, just 60 kilometers southwest, at Princeton University, a brilliant theorist named Robert Dicke, along with his formidable team including Jim Peebles, P.J.E. Roll, and D.T. Wilkinson, was working on a parallel yet diametrically opposite quest. They were not trying to eliminate a signal, they were actively seeking one. Dicke's group had independently theorized the existence of a cosmic relic, a faint, lingering echo from the universe's earliest moments, a remnant radiation from the Big Bang. They were diligently constructing their own specialized radiometer, a device designed precisely to detect this theoretical phenomenon, this ancient whisper from creation itself. The stage was set for one of the most remarkable juxtapositions in the annals of science. Two teams, separated by a mere drive, yet worlds apart in their intentions. On one side, Penzias and Wilson, diligently trying to erase a noise, stumbled upon the most profound signal in cosmology. On the other, Dicke and his colleagues, knowing exactly what they were looking for, were on the precipice of building the instrument that would find it. The resolution of this incredible scientific race, however, was not a dramatic breakthrough captured on a complex array of detectors, but a simple phone call. Bernard Burke, a mutual colleague, connected the two groups, bridging the gap between an engineering nuisance and a cosmic revelation. This human side of discovery is often overlooked. The initial confusion, the shared perplexity, and the eventual collaboration exemplify the true spirit of scientific inquiry. Penzias and Wilson, initially baffled by their excess antenna temperature, found their inexplicable noise perfectly matched the theoretical prediction of Dickey's team for the cosmic microwave background. The two teams, recognizing the immense significance of this accidental alignment, published their findings back-to-back in the Astrophysical Journal, a testament to their mutual respect and the power of shared knowledge. What began as a frustrating, mundane problem in radio engineering, a persistent hiss that stubbornly refused to disappear, unexpectedly provided the first undeniable hard evidence for the Big Bang theory. It transformed cosmology from a realm of speculative philosophy, where theories were debated without concrete proof, into a precision observational science, forever altering our understanding of the universe's fiery birth. We have learned of the faint cosmic whisper that forever changed our understanding of the universe. But if that persistent hiss was the echo of creation, what did the universe actually sound like in its infancy? Before there was light, before stars ignited or galaxies coalesced, the cosmos was a realm not of silent void, but of profound, primordial sound. It was an echoing pressure cooker, filled with a searingly hot, incredibly dense plasma, a cosmic soup of protons, electrons, and photons, all locked in an inescapable, turbulent dance. Imagine, if you will, not a silent expansion, but a vast, resonant chamber, vibrating with the very forces that would sculpt all existence. This is the stage for a cosmic symphony, where the Big Bang itself was the initial, explosive downbeat, setting off a chain reaction of immense sound waves. For the first 380,000 years of its existence, the early universe was a maelstrom of competing forces: gravity, eternally striving to pull matter together into denser clumps, and radiation pressure, pushing outward with tremendous force, seeking to disperse everything. These opposing pressures created monumental ripples, vast propagating waves of density that sloshed through the plasma like an ocean across an infinite shore. These were not sound waves as we perceive them with our ears. There was no air to carry vibrations, no medium in the way we understand it. Instead, these were oscillations in the cosmic plasma itself, gargantuan fluctuations in pressure and density. Their fundamental frequencies and their overtones, much like the distinct pitch and resonance of a drum, were determined by the precise physical ingredients of that young cosmos. The size of the drum and the tension of its skin dictated the notes played in this grand cosmic overture. Every peak represented a region where gravity had momentarily won, pulling matter in, only for the radiation pressure to push it back out, creating a trough. This rhythmic expansion and contraction was the universe's first, deepest song. The theoretical framework for understanding these remarkable acoustic waves owes much to the groundbreaking work of two brilliant minds: the Soviet physicist Yakov Zeldovich and the Canadian-American cosmologist Jim Peebles. In the late 1960s and early 1970s, they pioneered the mathematical models that showed precisely how these baryon acoustic oscillations, or BAOs, would imprint a characteristic, measurable pattern not only on the nascent cosmic microwave background radiation, but also, critically, on the subsequent large-scale distribution of galaxies we observe today. Their insights were a revelation, transforming abstract ideas into concrete, testable predictions. Then came the pivotal moment, known as recombination. After 380,000 years, the universe had expanded and cooled just enough, from temperatures soaring into the billions of degrees down to roughly 3,000 degrees Kelvin, for electrons to finally combine with protons, forming stable, neutral hydrogen atoms. This was a cosmic liberation. Suddenly, the photons, previously trapped and scattering constantly off free electrons in the plasma, were free to travel unimpeded. This instant marks not just the birth of the cosmic microwave background photograph, the ancient image we discussed earlier. It was the precise moment the cosmic symphony was literally frozen in time. The peaks and troughs of those vast sound waves, those density ripples, were preserved as infinitesimally tiny temperature fluctuations in the newly released light. These ancient harmonics, these frozen echoes of the universe's earliest vibrations, were far more than just relics. They were, in essence, the gravitational seeds for all modern structures. The regions that were slightly denser, the peaks of those ancient sound waves, exerted a stronger gravitational pull, slowly but inexorably attracting more matter over billions of years. This process led to the formation of the first stars, then galaxies, and eventually the colossal galaxy clusters and superclusters that filament the cosmos today. This means that the sprawling architecture of the universe, the precise placement of immense galaxy clusters across the vast cosmic web, is, in its very essence, a visible echo of a sound they can no longer hear. It is the lingering imprint of a song played at the dawn of time, written into the very fabric of space itself. We have journeyed back to the universe's infancy, witnessing its fiery birth and hearing the primordial sound waves that echoed through its first 380,000 years. We have seen how light, finally freed from the dense plasma, painted the earliest portrait of existence, the cosmic microwave background. But this ancient image, this faint glow still permeating the cosmos, is far more than a beautiful relic. It is the ultimate arbiter of cosmic truth, a definitive, unforgiving test that any theory about our universe's origins must pass. It acts as a kind of celestial lie detector, a cosmological forgery detection kit. Consider this. Before the 1990s, the grand narrative of the cosmos was a fiercely contested battleground. On one side stood the ascendant, yet still debated, Big Bang theory, positing a universe that exploded into being from an incredibly hot, dense state and has been expanding and evolving ever since. On the other, its most formidable rival was the elegant, steady-state model. Proposed in 1948 by brilliant minds like Fred Hoyle, Hermann Bondi, and Thomas Gold, this theory painted a picture of an eternal, unchanging universe, one that had no beginning and would have no end. It suggested that new matter was continuously created, just enough to fill the gaps left by expansion, maintaining a constant density and appearance throughout time. The universe, according to steady state, looked much the same yesterday, today, and forever. The accidental discovery of the cosmic microwave background's uniform temperature in 1964, that persistent hiss detected by Penzias and Wilson, delivered a significant blow to the steady-state model. A universe that had always been the same should not possess a relic of a hot, dense beginning. However, the steady-state model was resilient. Its proponents argued that the CMB might be explained by other, less revolutionary phenomena. The real, decisive moment, The final, crushing blow arrived with NASA's Cosmic Background Explorer, or COBE, satellite. Launched in 1989, COBE was specifically designed not just to measure the CMB's overall temperature, but to search for something far more subtle and profound: the minuscule temperature variations, the anisotropies, predicted by the Big Bang model. The pressure on COBE's principal investigators, George Smoot and John Mather, and their entire team was immense. This wasn't just another scientific experiment, it was a high-stakes investigation into the very fabric of reality. The Big Bang theory absolutely required these tiny fluctuations. Without them, the universe would have remained perfectly uniform, without any gravitational seeds to ever form stars, galaxies, or indeed us. Finding these variations was akin to finding the primordial blueprints for every structure in the universe. Not finding them would have meant the Big Bang model in its current form was fundamentally flawed. Then came the dramatic announcement in 1992. The results were in. The COBE data revealed the anisotropies, those tiny hot and cold spots in the cosmic microwave background, exactly as predicted by the Big Bang. George Smoot famously declared, and many remember the quote, "If you're religious, it's like looking at God." This was not a theological statement, not an endorsement of any particular faith. Rather, it was a scientist's awestruck recognition of the profound, almost unbelievable perfection with which the measured data aligned with the theoretical predictions. It was a moment of scientific epiphany, a confirmation that resonated with a cosmic echo. How precise were these measurements? The temperature variations COBE detected were incredibly small, on the order of just a few parts in 100,000 Kelvin. Imagine the average temperature of the entire universe is like a vast ocean, and these variations are ripples on its surface no taller than a single molecule. Yet, it was these infinitesimally small differences, these subtle peaks and troughs of energy, that held the universe's deepest secrets. The precise statistical properties of these hot and cold spots, their average size, their distribution across the sky, their characteristic pattern in what cosmologists call the power spectrum, provided an unforgeable signature of our universe's fundamental parameters. This signature is like the universe's cosmic DNA. From it, scientists can precisely determine the universe's age, down to tens of millions of years within a 13.8 billion year span. They can deduce its geometry, whether it is flat, curved like a sphere, or open like a saddle, with an accuracy of better than 0.5%. They can unravel its composition, telling us the exact proportions of ordinary matter, dark matter, and dark energy that make up the cosmos. Any alternative theory that cannot precisely replicate this intricate, almost impossibly detailed signature is immediately, definitively ruled out. The cosmic microwave background, in its serene and ancient glow, stands as the ultimate guard against cosmological speculation, transforming the sprawling, often philosophical field of cosmology into a rigorous precision science. The cosmic microwave background, that faint, ancient glow permeating the cosmos, is often celebrated as the universe's first photograph. It is the image of creation, frozen in time, a testament to the Big Bang. But what if this cosmic relic is more than just a picture? What if it is a profound Rosetta Stone, holding clues that unlock secrets far beyond the universe's grand narrative, translating between realms of physics once thought entirely disconnected? This ancient light, born nearly 14 billion years ago, carries incredibly subtle properties, nuances that cosmologists are only now beginning to fully decode. Chief among these is its polarization. Consider a light wave. Like a ripple on a pond, it oscillates. But unlike a simple ripple, light can oscillate in various directions perpendicular to its path. When these oscillations prefer a certain direction, we say the light is polarized. The cosmic microwave background's light, despite its vast journey, retains specific patterns of polarization, acting as a cosmic fingerprint. Scientists categorize these patterns into two main types, E modes and B modes. E-mode polarization patterns are like swirling whirlpools or radial lines, originating from the compression and rarefaction of the early universe's plasma, the very same density fluctuations that Kobe first detected. These E-modes are what we expect from the standard evolution of the cosmos, a predictable signature of the universe's early acoustic symphony. But it is the B-mode polarization, a more complex, twisting, curl-like pattern that holds the potential key to one of the most elusive phenomena in all of physics. These B-modes, if they exist with a primordial origin, would be the unique and definitive signature of gravitational waves, ancient ripples in space-time itself, generated during a hypothetical period known as cosmic inflation. This was an epoch of exponential expansion, occurring just a tiny fraction of a second after the Big Bang, stretching the universe faster than any human mind can truly grasp. During inflation, the universe expanded by a factor of at least 10 to the power of 26, meaning a region the size of an atom could have swelled to the size of a galaxy in less than a trillionth of a second. Such a violent, rapid expansion would have shaken the very fabric of space-time, producing gravitational waves that would leave their indelible mark as B-mode polarization on the cosmic microwave background. Detecting these would not just confirm inflation, it would open a direct window into the physics of the universe's absolute first moments, an energy regime far beyond anything terrestrial accelerators could ever hope to achieve. The quest to find these primordial B-modes led to high-stakes scientific drama. In 2014, the BICEP-2 experiment, located at the frigid geographic South Pole, announced a groundbreaking discovery. Their team, braving temperatures that could plummet to -90°C, claimed to have detected the elusive B-mode polarization pattern, seemingly confirming the existence of primordial gravitational waves and providing direct evidence for cosmic inflation. The news sent shockwaves through the scientific community. George Smoot, the Nobel laureate from Kobe, even described it as Nobel Prize worthy. It was a moment of immense excitement, a potential glimpse into physics at energy scales so high, so fundamental, they bordered on the unimaginable. Yet science, at its core, is a rigorous process of self-correction. Within months of the BICEP-2 announcement, a different picture began to emerge. Subsequent analyses, particularly those combining BICEP-2 data with observations from the European Space Agency's Planck satellite, revealed a sobering truth. The signal BICEP-2 had detected, while undeniably real, was far more likely to be contamination from galactic dust, tiny, elongated grains of material within our own Milky Way galaxy, that emit polarized light, mimicking the very B-mode pattern cosmologists were searching for. It was a perfect, albeit humbling, case study in the scientific method's relentless pursuit of truth, initial excitement giving way to critical scrutiny, leading to retraction, all in the service of greater accuracy. The search for primordial B-modes continues today, a testament to the scientific community's unwavering commitment to verifiable evidence. But the cosmic microwave background's utility as a Rosetta Stone extends even further, touching upon the universe's most mysterious components. As the light from the CMB travels across billions of years to reach our detectors, it interacts with the universe's large-scale structures, colossal clusters of galaxies, vast voids, and the invisible scaffolding of dark matter that binds them together. This interaction manifests as an effect known as gravitational lensing. Much like a distant star's light is bent and distorted by the gravity of a massive galaxy lying in between, the CMB photons are subtly warped and redirected by the gravitational pull of everything they pass through. By precisely measuring these minute distortions in the CMB's patterns, cosmologists can effectively map the distribution of dark matter across the vast cosmic web. Dark matter, that enigmatic substance that makes up roughly 27% of the universe's mass but does not interact with light, is otherwise invisible to us. Yet, its gravitational influence is profound. The cosmic microwave background, acting as a cosmic backlight, allows us to literally see its gravitational shadows, creating highly detailed maps of where this hidden mass resides. These maps are invaluable for understanding how structures formed in the universe and for testing our fundamental models of cosmology. Furthermore, this ancient light provides crucial insights into the properties of the universe's most elusive particles, neutrinos. Once thought to be massless, these subatomic particles, billions of which stream through your body every second, possess an incredibly tiny, non-zero mass. The total mass of all neutrinos in the universe, though individually minuscule, has a subtle yet measurable impact on the universe's expansion and the growth of cosmic structures. By analyzing the fine details of the cosmic microwave background, particularly through its gravitational lensing patterns, scientists can place incredibly precise constraints on the total mass of neutrinos. These constraints are vital for particle physics, testing the standard model and searching for new physics beyond it, bridging the gap between the largest observable scales in the universe and the smallest, most fundamental quantum phenomena. Thus, this ancient map of light is not merely a historical document. It is a vibrant, active laboratory, allowing us to test grand unified theories that seek to reconcile the fundamental forces of nature, to probe the physics of cosmic inflation, and to explore the properties of elementary particles in energy regimes that no terrestrial accelerator could ever hope to replicate. It is a cosmic bridge, connecting the infinitesimally small with the impossibly vast. To perceive the very first light from the infant universe, a faint echo from creation's dawn, we must confront an unexpected obstacle, the swirling, vibrant tapestry of our very own cosmic home, the Milky Way galaxy. It is as if we are attempting to capture a whisper from across a vast chasm while standing in the midst of a roaring, bustling city. This isn't merely a nuisance for cosmologists. It is an extraordinary scientific challenge that, in its overcoming, has gifted us some of the most intricate and revealing maps of our own galactic backyard ever conceived. The light from the cosmic microwave background, having journeyed for nearly 14 billion years, finally reaches us. But first it must pass through the dense, active environment of our galaxy. This galactic fog is not uniform. It comprises several distinct forms of electromagnetic radiation, each painting its own layer of interference across the sky. Think of it as trying to see a delicate, ancient fresco through multiple layers of dynamic, glowing veils. One such veil is synchrotron radiation, emitted by electrons spiraling at near light speed within the Milky Way's powerful magnetic fields. These electrons, accelerated by cosmic rays, create a diffuse, energetic glow that can easily overpower the faint, ancient signal we seek. Another significant contaminant is the thermal emission from interstellar dust grains, tiny particles scattered throughout the galaxy that are warmed by the relentless starlight. These dust grains absorb light from stars and then re-emit it at longer wavelengths, primarily in the infrared and microwave portions of the spectrum, precisely where the cosmic microwave background resides. This is akin to trying to discern a distant star's twinkle through the heat haze rising from a vast, warm desert floor. And then there is the free emission, generated when free electrons in hot, ionized gas clouds scatter off protons, producing their own distinct radio waves. These are like localized, glowing pockets of cosmic plasma, contributing to the overall cacophony of galactic light. The monumental task of peering through these glowing layers fell to the European Space Agency's Planck satellite team, a dedicated cohort of scientists and engineers who operated their extraordinary instrument from 2009 to 2013. Their challenge was immense, to meticulously peel away these layers of local galactic light from the ancient, incredibly faint cosmic microwave background signal. This required not just cutting-edge hardware, but the development of highly sophisticated component separation algorithms, complex mathematical tools designed to distinguish and isolate different sources of radiation based on their unique spectral signatures. Imagine attempting to isolate the specific notes of a distant, ancient melody from a symphony orchestra, where every instrument is playing at full volume. The successful implementation of these algorithms led to a dual triumph, a scientific achievement of breathtaking scope. Not only did the Planck team produce the most precise all-sky map of the cosmic microwave background to date, revealing the infinitesimally tiny temperature fluctuations that encode the universe's earliest moments, but in doing so, they also created unprecedented, razor-sharp maps of our own Milky Way galaxy. These galactic maps detail the intricate structure of its magnetic fields, the precise distribution of its interstellar dust, and the varying temperatures of its gas clouds. For astrophysicists, this was an unexpected bonanza, providing a portrait of our galactic home sharper than any seen before. When you observe these stunning visualizations derived from the Planck data, the galaxy reveals itself in a new light. Literally, one can discern intricate filaments of gas and dust, previously invisible, stretching for hundreds of light years, tracing the pathways of stellar nurseries. You can clearly see magnetic loops, vast arcs of energy and matter, influencing everything from star formation to the dynamics of spiral arms. These maps have provided crucial, invaluable data for astrophysicists who labor to understand the complex processes of how stars are born, how galaxies evolve, and how magnetic fields shape the cosmic environment. This entire endeavor reveals a beautiful synergy inherent in scientific exploration. The profound quest to understand the ultimate origin of the cosmos inadvertently bestowed upon us the sharpest ever portrait of our own galactic home. The cosmic microwave background, that ancient light from the universe's infancy, paints a nearly flawless portrait of creation. It is a canvas of uniform, primordial glow, marked only by the faintest ripples of temperature variation, the very seeds of galaxies. Yet, within this exquisite cosmic tapestry, one feature stands out, an anomaly that has challenged our understanding and pushed the very limits of statistical probability. It is known as the CMB cold spot, and it is far more than just a cosmic quirk. It is a fascinating case study at the intersection of immense data and the curious workings of the human mind. This cold spot is exactly as its name suggests, a region of the sky that is both anomalously large and unusually cold when compared to the predictions of our standard cosmological model. Detected by the Wilkinson Microwave Anisotropy Probe, or WMAP, and later confirmed with even greater precision by the European Space Agency's Planck satellite, this vast expanse of space, roughly 20 degrees across, or about 40 times the apparent width of a full moon, registers a temperature slightly cooler than its surroundings. We are talking about differences of mere microkelvin, fractions of a degree above absolute zero, yet these tiny variations become stark anomalies when measured across billions of light-years. It's a cosmic bruise on the otherwise smooth face of the infant universe, a slight, almost imperceptible shiver in the grand cosmic design. The leading scientific explanation for this immense cold patch is, perhaps, surprisingly mundane. It proposes that the cold spot is simply a statistical fluctuation, an unlikely but entirely possible arrangement in a random field of data. Think of it like this. If you were to flip a coin 1,000 times, you would expect roughly 500 heads and 500 tails. But it is entirely possible, though extremely improbable, that you might get a streak of 20 tails in a row. The cold spot, according to this view, is that improbable streak of tails on the cosmic coin, a 1 in 1,000 chance that simply manifested in our observable universe. It does not defy the laws of physics, it merely stretches the boundaries of what is statistically expected. But for scientists, the allure of the unusual is often irresistible, and so more speculative yet physically plausible hypotheses have been advanced to explain the cold spot. One intriguing idea, championed by physicist Laura Mersini-Houghton, posits that this cold region could be a bruise left by a collision with another bubble universe. In the theoretical framework of the multiverse, our universe might be just one of countless cosmic bubbles, constantly inflating and occasionally bumping into each other. Such a collision could, in theory, leave an imprint on our universe, manifesting as a large, cold area in the cosmic microwave background. It is a concept that truly bends the mind, suggesting our universe might not be an isolated island, but part of a grander, more populated cosmic ocean. Another compelling hypothesis suggests the cold spot is caused by a massive supervoid, an enormous region of space remarkably empty of galaxies, dark matter, and other cosmic structures. Light from the cosmic microwave background passing through such a void would experience a subtle cooling effect. As photons enter the supervoid, they lose a tiny amount of energy as they climb out of the gravitational potential well of surrounding matter. While this effect is usually negligible for individual photons, a void of truly colossal scale, perhaps hundreds of millions of light-years across and nearly devoid of matter, could cumulatively cause the observed cooling. This theory, unlike the multiverse collision, keeps us firmly within the confines of our own universe, albeit one with surprisingly vast empty spaces. Yet, as we delve into these anomalies, we must confront a fundamental aspect of human cognition, the brain's innate tendency for apophenia. This is the cognitive bias of seeing meaningful patterns in random data, a deeply ingrained trait that has served us well throughout evolution. It is why we so readily see faces in the swirling clouds above, or discern mythical creatures and ancient heroes in the scattered patterns of distant stars that form our constellations. This tendency to find order in chaos, to seek out significance in the statistically mundane, is a powerful driver of both discovery and misinterpretation. Even scientists, armed with the most sophisticated statistical tools and decades of rigorous training, are not immune to the seductive allure of an anomaly. The human brain craves narrative. It seeks causes and effects, and a seemingly inexplicable cold spot in the universe's oldest light can trigger an almost primal urge to find a profound explanation. Psychologists like Daniel Kahneman have extensively documented how our cognitive biases shape our interpretation of complex data, even when we believe we are being purely objective. The cold spot, therefore, serves as a powerful reminder that scientific inquiry is not just about crunching numbers. It is also about understanding our own human biases, ensuring that our search for cosmic truth remains grounded in evidence, even when the universe throws us an intriguing curveball. To truly capture a photograph of the infant universe, to discern the faint, ancient glow of the cosmic microwave background, our civilization demands more than just sophisticated telescopes. It requires instruments pushed to the very precipice of engineering, devices so exquisitely sensitive they redefine the boundary of what is technologically feasible. This audacious quest to peer into the universe's genesis has, unexpectedly, forged a lineage of innovation, sparking breakthroughs that ripple far beyond the realm of astrophysics, profoundly impacting our daily lives in ways few would ever anticipate. At the very heart of these cosmic observatories, whether soaring above Earth on satellites or perched on remote mountaintops, lie the detectors. These are not merely cameras. They are cryogenic eyes, designed to register the faintest whisper of microwave radiation that has journeyed for nearly 14 billion years across the cosmos. Consider for a moment the incredible challenge to detect a signal so weak, a warmth so infinitesimal, that it requires instruments to be cooled to mere fractions of a degree above absolute zero. That is a temperature of approximately 0.05 Kelvin, a frigid extreme colder than the most distant, desolate corners of interstellar space, a temperature where even atoms barely vibrate. To achieve this almost unimaginable chill, scientists employ cutting-edge technologies like superconducting transition-edge sensors, often called TS detectors, and kinetic inductance detectors, known as KIDs. These tiny, intricate devices harness the quantum world, relying on the bizarre properties of materials when cooled to such extreme limits. At these ultra-low temperatures, certain materials become superconductors, meaning their electrical resistance vanishes entirely. This allows them to register the tiniest energy fluctuations from incoming photons, effectively amplifying the faint microwave glow of the cosmic microwave background into a detectable signal. It's like trying to weigh a single feather on a scale designed for elephants, yet achieving the precision of a jeweler's balance. The engineering marvels behind this extreme cold are equally impressive. The development of advanced cryogenics, particularly dilution refrigerators, has been absolutely instrumental. These complex systems use a mixture of helium-3 and helium-4 isotopes to create a continuous cooling cycle, lowering temperatures step by precise step, far beyond what liquid helium alone could achieve. This expertise, honed in the pursuit of cosmic truth, has not remained confined to astrophysics laboratories. It has, in fact, catalyzed transformative advancements in medical imaging technologies. Magnetic resonance imaging, or MRI, machines, which save countless lives by providing unparalleled views inside the human body without invasive surgery, rely fundamentally on powerful superconducting magnets. These magnets, chilled by liquid helium, generate incredibly strong, stable magnetic fields essential for imaging soft tissues. Similarly, magnetoencephalography, or MEG, another advanced brain imaging technique that maps neuronal activity by detecting magnetic fields produced by electrical currents in the brain, also depends on highly sensitive superconducting quantum interference devices, or SQUDs, which demand ultra-cold environments achieved through the very same cryogenic principles pioneered for cosmic observation. Beyond the hardware, the sheer computational challenge of processing the gargantuan datasets generated by these experiments has driven another wave of innovation. Observatories like the Planck satellite, for instance, generated petabytes of noisy raw data, an amount equivalent to hundreds of millions of high-definition movies. Sifting through this cosmic static to extract the faint, meaningful signals from the dawn of time is a task beyond human capability, demanding novel data analysis algorithms and sophisticated machine learning techniques. These are not just statistical tools, they are artificial intelligences trained to discern patterns where none seem to exist, to clean noise from chaos. And astonishingly, these very same statistical methods, originally designed to reconstruct the universe's earliest moments, are now finding critical applications in entirely different fields. They are being adapted for use in financial modeling, helping to detect subtle trends and anomalies in volatile markets. They are revolutionizing weather prediction, allowing meteorologists to process vast atmospheric data and create more accurate, long-range forecasts. And they are even transforming genomics, aiding scientists in identifying complex patterns within DNA sequences to understand diseases and develop new therapies. Consider the ongoing work at ground-based observatories like the Simons Observatory, perched high in the Atacama Desert of Chile, with its pristine, dry air offering an unparalleled view of the microwave sky. Or the ambitious future CMB-S4 project, a next-generation endeavor planning an array of telescopes in that same remote, high-altitude desert. These are not just isolated scientific experiments, they are colossal engines of technological progress. Their relentless pursuit of the universe's most ancient light propels the boundaries of human knowledge and engineering, creating an unexpected tide of benefits that ripple throughout society, shaping our world in unforeseen, profound ways, extending the reach of our cryogenic eyes far beyond the cosmos. We have journeyed through the universe's fiery dawn, decoded the whispers of its infancy, and seen how the cosmic microwave background acts as creation's first photograph. But what if this profound message, this ancient light that still permeates the cosmos, is not eternal? What if the universe's most eloquent echo is destined to fade, a fleeting message that we are uniquely positioned to hear? This final chapter reveals a sobering truth. The cosmic microwave background is a transient phenomenon, a temporary beacon in the vastness of cosmic time, and our ability to perceive it marks a privileged, perhaps singular, moment in the universe's sprawling history. The reason for this cosmic evanescence lies in the very engine of our universe's evolution, the accelerating expansion, driven by the enigmatic force known as dark energy. This mysterious component, which makes up roughly 68% of the universe's total energy density, acts like an anti-gravitational force, pushing galaxies apart at an ever-increasing rate. As the universe inflates, stretching space itself, the photons that comprise the cosmic microwave background are also stretched. Consider these photons as tiny waves on an ever-expanding rubber sheet. As the sheet grows, the waves grow longer, their wavelengths constantly increasing. This relentless stretching, known to physicists as redshift, has a profound effect on the cosmic microwave background photons. As their wavelengths lengthen, their energy decreases, causing them to cool down and shift to ever lower frequencies. What we currently detect as a faint microwave glow, with a precise temperature of about 2.725 Kelvin, will, over unfathomable eons, cool to mere fractions of a degree, then to picokelvin, and eventually become indistinguishable from the background noise. It is like listening to a distant radio signal that is not only getting fainter, but also shifting to frequencies your receiver can no longer tune into, making it progressively harder, then utterly impossible, to detect. Peering far into the cosmic future, beyond billions, even trillions of years, cosmologists have contemplated a scenario known as the end of cosmology hypothesis. This provocative concept was seriously considered by eminent physicists such as Lawrence Krauss and Robert Caldwell. They painted a stark picture of a universe utterly transformed, a future where the very foundations of our current understanding of the cosmos might vanish from observable reality. It is a thought experiment that forces us to confront the limits of our knowledge and the transient nature of even the most fundamental cosmic evidence. In this distant epoch, the accelerating expansion will have pulled all but the most gravitationally bound structures completely out of view. Our local group of galaxies, a modest collection including the Milky Way, Andromeda, and a few dozen smaller galaxies, will remain gravitationally tethered. But all other galaxies, every other cosmic island beyond this small cluster, will have receded past what scientists call our cosmic event horizon. Once a galaxy crosses this threshold, its light, no matter how bright, can never again reach us. They will become forever invisible, swallowed by the relentless expansion of space, leaving our descendants gazing into a sky populated by only a handful of nearby stellar systems. And the cosmic microwave background itself will suffer a similar, irreversible fate. Redshifted to an extreme degree, its already faint signal will be stretched to wavelengths so long, its energy so minuscule, that it will become practically undetectable against the natural background noise generated even by our own galaxy. Imagine trying to hear the faintest whisper of a primordial echo while standing directly beside a roaring waterfall. Future intelligent civilizations, if they arise in that isolated and seemingly static cosmos, would possess no observational evidence of the Big Bang, no direct proof of the universe's fiery birth, no lingering trace of its initial expansion. The night sky, devoid of distant galaxies and the ancient afterglow, would offer them no clues, no cosmic breadcrumbs leading back to creation. They would exist in a state of profound cosmic ignorance, trapped within a small, seemingly unchanging island of matter, with no way to deduce the grand cosmic drama that preceded their existence. There would be no distant galaxies to measure for expansion, no faint microwave glow to trace back to a primordial plasma. Their science, no matter how advanced, would be limited to their immediate cosmic neighborhood, forever cut off from the universe's true history, leaving them with an unescapable existential puzzle. This is not presented as a doomsday prediction, a chilling prophecy of cosmic doom, but rather a powerful, humbling reflection on our unique place in time. We, as a civilization, stand in a remarkably special, perhaps even singular, window of cosmic history. We live at a time when the universe has expanded enough for the cosmic microwave background photons to cool and stretch into the microwave range, making them detectable by our technology, yet not so much that they have redshifted beyond all recognition. The echo of creation is still audibly resounding across the cosmos, and, crucially, we possess the scientific means to listen. This imbues our quest for knowledge with a profound sense of urgency, reminding us that the universe is not a static painting, but a dynamic, evolving masterpiece whose grandest secrets might not always be available for us to discover. It is a call to listen closely, to explore relentlessly, while the ancient light still shines.